Bismillahirrahmanirrahim. Assalamu alaikum. In the today's lecture, we will be doing two examples related to the dynamic force analysis using the graphical method. In the first example, it is stated as for the mechanism shown, determine the force Fa. This is the force Fa for dynamic equilibrium at a constant velocity Va equal to 12.5 foot per second. This is Va 12.5 foot per second. Link 3, the weight of link 3 is 2.2 lbf, and Ig3, the moment of inertia about the gravitational center, is equal to 0.0479 lb in second square. Linkage is in horizontal plane, neglect the fraction. AB equal to 10 inch, GA, this is GA is equal to 5 inches, AO equal to 8 inches, and OB equal to 6 inches. We are given the acceleration polygon. We will be using this acceleration polygon as already, if you remember, when we were solving at the example related to the during the analytical force analysis, we were using the acceleration polygon in order to calculate the inertial forces and the inertial moment. So here we will also using the inertial this acceleration polygon in order to calculate the inertial forces and the inertial moment. Okay, so if you can see in this problem over here, like the force Fa is unknown. Okay, so we will start from link 3. If you can see in the link 3, the acceleration polygon, it is giving the complete information related to the link 3. You can see the acceleration BA, B with respect to A tangential, so this is BA is basically for link 3. Similarly, the BA radial, you can say the normal component along the radial direction and along the normal direction, it's also given for the link 3. And similarly, the AG, G point is on the link 3, so AG is also given to us. So the complete information is given related to the link 3. So we can start from here and we can go up and we can calculate the value of Fa. Okay, so let's see which forces are acted upon the on the link 3. Okay, so if you can see, before calculating the forces, the inertial forces and the inertial moments on link 3, we should have the value of the angular acceleration. As you know that the tangential velocity is equal to r omega, so tangential acceleration is equal to r alpha. So from here we have the tangential acceleration component for link 3, and also we have the length of link 3. So from here we can find alpha 3. So we will calculate alpha 3, and then we will come towards the mass. So already we are given the weight, so we will divide the weight in lbf divided by g, the gravitational constant. So from here we will get the value of the mass. So now you know that the force, the inertial force is equal to ma. So we have m, also we have the acceleration ag. So when we multiply m by a, so it will give us the inertial force. Over here you need to remember one thing, that the inertial moment about the center of gravity, it will be equal to the Ig3, or the Ig multiplied by the alpha 3, Ig3 multiplied by alpha 3. So this moment should be equal to the like we can stabilize, or we can cancel this moment when we multiply the inertial force. Let's suppose if the inertial force is applied at a certain distance, okay, such that it is with the moment arm of h is the distance from the gravitational center. So the ma, the inertial force, multiplied by h, it will create a moment such that it will neutralize, or it will become equal in an opposite direction to the moment created at the center of gravity due to this body. Okay, so from here we can find the h. Okay, So how we can find the H? Because we need the location where this force will be acted for the dynamic equilibrium of this body. Okay, so you should remember this thing. Sorry, you should remember this thing, like in the graphical analysis for the dynamic force analysis. In almost in each and every problem, you need to find this H, that where will be the inertial force acting, because in the force polygon we need the inertial force, and where it will be acting you can know it from the value of H, where H is the distance from the center of gravity of that specific length. Okay, so over here we know Ig, we have alpha 3, we have m3, and we have Ag, so we can calculate the value of H. And what is the H? H is this distance. Okay, so you see that H is the distance starting from G until here, this distance is H. So if you can see the link 3, basically this is a 3-force member. One force is the inertial force. Okay, one force is acted upon C from link 4. Okay, one force is acted upon link 3 from link 2. So in order for link 3 to be in the equilibrium, all these 3 forces should intersect each other at a point that is, we already know that point, that is concurrency point. Okay, but in order to find the concurrency point, you should keep in mind that one of the force should be completely known, its magnitude and its direction, and for the other force the direction should be known. So in that case, if you have these two conditions, one of the force should be completely known, and the other force, for the other force, if you have only the direction is known, okay, the line of action is known, then you can calculate in the 3-force member, you can calculate all the forces graphically. Okay, so here the known force is the inertial force. Once you have H, so the point of application of this force is known to you, that where it will be applied. So you can see once you have H, so you know that the gravitational force, that is minus MAG, it will be applied in this direction. So this is the line of action of the gravitation force. Similarly, you know that the force that will be exerted from link 4 to link 3, it will be in the vertical direction, because the force exerted from link 4, it will be in the vertical direction. Similarly, the force, once you have this intersecting point, so the only thing is the third force, in this 3-force member, it will come from link 2 to link 3, and it will be also passing from the concurrency point that we already have calculated. So in this case, the magnitude of the force, the inertial force, was known to us. Similarly, the direction of the force from link 4 to link 3 was known to us. Okay, and similarly, we can have a force, we can directly connect a force starting from the link 2 until the concurrency point. So knowing these three, we can how we can calculate the value of Fa. If you can see that the line of action of, here we have two forces, one force is Va, okay, sorry, one force is Fa in the vertical direction, and the other force is actually acted from link 1, that is the ground link, on link 2. Okay, so we have two forces over here, that is the vertical force, and we have one force over here. So if you can see over here, just see over here. So in this body, if you can see over here, okay, so can you see here, like the line of action of the force, that is by using the parallelogram theorem, if you add F with F12, okay, so their addition is Fa plus F12. This is the line of action is similar, it is also passing from the concurrency point. It means if you add F14, so F14 plus MAG is equal to if a plus if12. Similarly, if a plus if12 is also equal to if a plus if12. So in this question, if a was required, so if we know if 1 4, then it's equal in opposite to the if a. Okay, and over here you know that we know the line of action and the magnitude of MAG. Okay, so if you draw the MAG starting from the concurrency point, then you know you know the line of action for the this force that is acted from length 2 to length 3, and you also know the vertical, you know that the if14 has the vertical direction. So just this is just for you people as a practice. Okay, so over here we have one force is completely known, that is the inertial force MAG, and its direction is known. For the other force, that is F14, the direction is known. Okay, and then the only thing is, once you have the concurrency point, you know you need to have a parallel line like this line. The F23 will be along this line. Okay, so from here you can calculate the value of F14, and once from this force triangle, when you calculate F14, so this F14 will be exactly equal to the FA. Okay, so this is how you can calculate the value of the unknown force FA. So in this problem you need to keep in mind how will you solve similar problem like this one. You need to keep in mind that whenever you have a link, let's suppose for this link the mass was given to us, the Ig was given to us. Okay, and we can easily calculate the value of alpha 3, and the weight was given to us, from which we calculate m3. So you can have the inertial force completely known, its location completely known, when you find the value of h. Okay, so for this you have to equate the inertial moment equal to the inertial force multiplied by h, and h is the distance from the gravitational point. Okay, so once you have the value of h, then the problem is easy. You can easily calculate the value of the unknown forces over here, and once you have all the forces known over here, then you can go toward the unknown forces that is required in this problem, and you can easily find them. Okay, so for this, first start by solving this force triangle. Once you have all the forces known over here, then you can come here and you can find the forces over here. Okay, so you can see over here, in order to find FA, you should know F14, and then F14 you can find once you have this you solve this force triangle. But keep in mind, whenever you are solving any force triangle, you need to have a scale. Okay, over here the known force is MAG. So MAG, once you have MAG, so just make your own scale. Okay, such that scale will be applicable for the whole problem, and then you can find the unknown force F14. And once you already you know the scale, so you will use the scale to calculate this value in the inches, and then you will convert it into the lbf, and the same value will be for FA, due to because the line of action of the resultant is same as the line of action over here. Okay, over here we have another problem. This problem is also related to the dynamic force analysis using the graphical method, but over here we are using the superposition method. Just this is like to give you a flavor of the superposition method. Basically, in the superposition method, we are not solving the whole force analysis for a link at once. So we will consider, let's suppose, this force, and then we will calculate, we will have the reaction forces for due to only this force. Then we will calculate, we will take only the inertial force due to the force MA, the inertial force due to the acceleration AG4. Okay, so So, and we will consider the inertial the reaction forces when we consider only the inertial force. We will not consider this one. And similarly the third case will be when we will not consider this force, and also we will not consider this force, and we will just imagine that this body, the link 4, is interaction with the link 3. So what will be the reaction forces? So this one link will be the force analysis will be a summation of the 3 force analysis. We will see it in the coming slide. So make a complete dynamic force analysis for the 4 link mechanism shown. This is the 4 link mechanism shown, link 2, 3, 4, and 1 is the ground link. Acceleration information is shown. Acceleration information in the dynamic problem, like solving by the analytical analysis or by the graphical analysis, the acceleration polygon will be given to you. You can have you can get the values from the acceleration polygon. Similarly, the dimension of the links are also given to us, and the weights are also given, because we will need the weights in order to calculate the value of masses. Okay, the mass of link 3, link 2, and link 4. Okay, so first we will, let's see, starting from link 4. Okay, as I told you, if you look here in the link 4, okay, a force Fc is applied at point C. Similarly, there will be an inertial force due to the there will be an inertial force, and also there will be forces due to the interaction with the link 3. Okay, and due to the interaction with link 3, and also with the interaction of link 4 with link 3, and then interaction of link 4 with the ground link 1. Okay, so let's see, starting from the first force, we will be adding these all the 3 in order to have the complete force analysis. Okay, so in the first case we are not considering the force Fc, and also we are not considering we are only considering, in the first case we are only considering the inertial force. So how we can calculate the point of application of the inertial force? So I told you in the previous problem, you need to find the value of h. Okay, so h over here will be Ig4 alpha 4 divided by m4 Ag4. As I told you, how this formula comes, from where it comes, Ig4 into alpha 4 is equal to the inertial moment, and m4 Ag4 into h4, it will also give you the inertial moment. So from here you can find the value of h4, and h4 is the distance from the gravitational point, you see, starting from here until here. So we already know from the acceleration polygon that Ag4 is in this direction, so the inertial force minus m4 Ag4 will be in the opposite direction. Okay, so over here, because it is a 3 force element, 3 force member, so we need to find the concurrency point. Once we have the concurrency, we find the concurrency point, so we can solve the fourth polygon in order to find all the force elements. Okay, so over here, this is the line of action. So the line of action and magnitude is known for the inertial force. Then the line of action of if 3 4 prime is known, because if 3 4 prime, it is coming from link 3, so we know the line of action that is coming toward B. So as we know from the previous example, if you know one of the force completely, if one of the force is completely known, that is m4 Ag4, that is completely known, its direction of action, line of action, and its magnitude is completely known. And for the other force, if you know the line of action, like in which direction it will occur. Okay, so this is known to us. So you see, this is known to us. So from there you can make you can connect this one with the tail of the inertial force, and the direction and the magnitude will also known for F1 4 prime. So once you solve this one, so you have these 3 components easily. Okay, now we will come to the second case, in which we are not considering the external force, and also we are not considering the inertial force. So in this case, if the link 3, it has, let's suppose if it is a force member, okay, let's suppose a 2 force member. So if there is no force of gravitational force, then it is a two force member, and these forces will be acted upon point B and point O4. So let's, the previous one was F1 F11 prime, so this will be F14 double prime and F34 double prime. The previous one was F34 prime. Now we will come to the third case, in which we will consider the external force Fc. Okay, so the external force Fc, we can calculate the external, we will only consider the external force Fc, and once you have Fc as, so then there will be two forces due to the interaction with the ground link, and also due to the interaction of the link 4 with link 3, and this will be a three force member, because we have two inertial forces, two reaction forces, okay, at B and at 4 O4, and also we have one external force. So this is a three force element, and there should be a concurrency point. So we know the magnitude and the line of action for Fc. This is known to us from the problem, and the magnitude is not known to us, but the we already know the direction of Fc. So direction of Fc is known, the direction of F34 is known. Once they intersect with one another, we can connect it with O4, and so we, from here we will get the complete triangle that we have over here. Okay, so Fc is already known to us, that is 40 lb, so we can scale it into inches, and over here we already know the direction, so we can draw, first we will draw Fc with our scale, and accordingly then we know the line of action of F34, so we will draw a parallel line starting from here, and then what we will do, we will draw another parallel line to F14 starting from the tail of Fc. So the point where they connect, intersect one another, so it will give us the magnitude of F14 double prime, triple prime, and F34 triple prime, and then we can use the value in inches to calculate the values in lb. So if you can see, this fourth triangle is completely known to us, this fourth triangle is completely known to us, but F34 double prime and F14 double prime is not known to us. So for this we can draw this, we can combine all these three to have this one, but over here F34 double prime is not known to us. So now we will come to the, this was only for link 4, now we will come to link 3, So in the case of link 3, we will do the same procedure, we will consider the three cases. In one of the case we will consider the inertial, only the inertial force, okay, and we will be having a concurrency point. In order to find the location of inertial force, so we need to find H3, so we will find H3 just like we have found H4, okay, and then once by the concurrency point you can solve this triangle, and you can find the F23 double prime and F43 double prime. So you see, if 34 double prime will be equal to F43 double prime, so it will make this this force and F14 double prime known to us, because F43 double prime is equal in magnitude with F34 double prime, and it should be equal to in magnitude with F14 double prime. So it means every force in this for link 4 in this system is known to us, everyone is known to us. Similarly over here, if you can see, over here we are considering the inertial force, so all the three components will be known to us. From here, when you don't consider the inertial force, and also you only consider this one, okay, F23 triple prime and F43 triple prime, so you already know from here that if 34 triple prime is known to us, so from we can take that value, the magnitude will be exactly same to this one, so this value will also be known to us, okay. So we can combine all these three cases, and all these three cases will come over here, so every component is known to us. So over here, if you can see, we have used the superposition principle, which states that the combination, like let's suppose on one link, if you are calculating the reaction forces, the total forces like that will be on that body due to more than one forces. So what you can do, you can consider one force at a time, and you can neglect the other forces at that time, and the effect due to the individual forces will be added, and it will give us the overall effect. So we done it for link 4, and then we done it for link 3. Now we will come to link 2. Okay, but you see the from here, once you have F34 known, okay, so once you done it for link 4, so it will give you F43. okay, similarly once you have F43 double prime known, so it will give you F34 double prime, and once you have F34 triple prime known, so it will give you F43 triple prime. Okay, so this is how in combination, when the two connected links, when you use the superposition principle with both of them, so they all the magnitudes of all the component of the reaction forces will be known to us. Okay, so now we will come to the final stage, because for the dynamic equilibrium all the forces should be known in this case. So you can see from here that the F23 prime is equal to F43 prime that we discussed over there, so it is known. F23 double prime is known, F43 double prime is known, F23 triple prime, F43 triple prime is known, and similarly the other forces are also known to us. Okay, so now the final thing is, if you can see from the problem, from here you will just see over here from the first slide, there should be a moment over here. As this body is rotating at a certain omega, it means some moment is applied over here. Okay, or this force is applied, so a moment will be created over here. This moment will be equal to a moment arm. There should be a force over here. This force will be F32, the force exerted from link 3 to link 2. F32 multiplied by h, it will give us that moment. So already we know this force, that is F32. So F32 we find it from the, once we have the free body diagram and the force analysis for link 3, so we come to know about F32. Okay, actually we find F23 from there when we have the force analysis from link 3, and we know that F23 is equal to F32. So from here we also have the line of action. So let's see what was the line of, we can see the line of action of you see F23. So F23 is in this direction. Okay, so the F32 will be in the opposite direction. So let's see from here, this is the direction of F32. Okay, starting from point A. So in order to cancel the effect of M12, in order for the body to be in the equilibrium, there should be another force, that is F12, such that the distance between these two, such that it will create a couple and it will cancel the effect of M12. The distance between these couple forces is H2 is equal to 1.56 inches. We will calculate it by scale. Okay, so now we can take the summation of moments at O2. So it will give us the value of M12, that is H2 1.56 inches, and to F32. F32 is already known to us. F23 and F32 will be same, that is 145 lb. Okay, so from here we can find the value of moment. So this was another example. You can redo this problem. Just try your best to do it again and to find that whether you are getting the same values or not. Okay, so this was just a flavor to give you a flavor for the problems related to the graphical analysis, graphical method during the dynamic force analysis. Okay, so try to solve these two problems, and if you have any problems, so we will discuss it during the lecture time. Okay, so